بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. In this tutorial lecture, we're going to provide a detailed example about how to make basic classification of multiple class of objects using Tensorflow 2.0 and Keras. And just for your information, that Keras was completely independent of Tensorflow, okay, for the version Tensorflow 1.0 or 1.x. And then with Tensorflow 2.0, it was integrated with Keras was integrated with Tensorflow. So in this version, we are going to use Tensorflow 2.0. Of course, the same tutorial, you can find it on Tensorflow documentation. Okay, it's called same thing, basic classification, classify images of clothing. But here in this notebook that I have sent to you, I have added a few more functionalities to make clear a few more concepts. Okay, so this guide trains a neural network model to classify images of clothing like sneakers, shirts, and we're going to provide the different steps to develop a classification project in TensorFlow 2 and Keras. Okay, so first of all, we make sure about the availability of TensorFlow version 2.0, and this instruction is only made in Google Colab. I mean, even if you don't make it in this notebook, if you use Jupyter Notebook with Anaconda, you don't need to use this statement. But if, for example, you use the Google Colab version, okay, and you can click here on Google Colab, you can do it online on Google Colab. So in this case, you will need this expression. Okay, then we will import the different libraries needed in the project. So the first library is the future module, and today I have sent you a video that explains the importance of this module, especially for the incompatibility between previous versions of Python and newer version of Python. I don't know if you have already seen the video, but if you don't, you can go to this link and you will see an example of the print function, okay, that is different in Python 3.6 and 2.7. And we can use the future module, import from the future module, in order to use the new functions into the older versions of Python. So this future module is done. So for example, if there is any change in the syntax in newer version and you are using an older version, you can use the future package to use the new definitions of the methods through the future package. And you can see more of the details in the YouTube video link presented above. And then of course, for any TensorFlow and Keras project, we need to import TensorFlow, and here we will denote it as TF. And also from TensorFlow module, we will import Keras. Okay, you can write just tf.keras, or if you do like this, you can just type Keras without using tf because it is already imported from the TensorFlow package. And we will work with NumPy arrays, so we import NumPy as MP, and matplotlib will be used for displaying the images. So matplotlib is actually the main library that is used to display images. And because there are different versions of TensorFlow, it's always good to check which version you are working on. And for example, in my case, I enable version 2. Okay, so you can open Anaconda, go to your environment. So here I'm using, this is the environment that I have named as TF2 to denote TensorFlow 2, but you can give it any other name. And here I'm using TF2 version, TensorFlow 2. So you can check here, or I will write TensorFlow. Okay, so it will give TensorFlow 2.0. If I go to this environment or to this environment, I will find TensorFlow 1.14 or a different version. Okay, so make sure that you are using the correct environment and the correct library, because there are differences in the syntax of TensorFlow 1.0 and 2.0. So in any deep learning project, first of all, we need to import the dataset. And here our dataset is the Fashion MNIST dataset, which contains 70,000 grayscale images divided into 10 categories. So unlike our previous example on cat classification, we had only one category to classify. So it's either 0 or 1. And we use the sigmoid function at the output layer. Now in this classification problem, we have 10 categories. So as you have already seen in the lecture, what output layer we are going to use? Here. Yeah, the softmax function. Okay, yes, the softmax function. And the images show individual articles of clothing okay, at low resolution. So here the resolution is only 20 pixel and 20 pixel. So you can consider fashion MNIST as another simple data set for entry level to test classification algorithms, whether they work fine or not. And you know that the basic data set for classification is usually the MNIST data set. And MNIST, it contains the numbers between 0 and 1. And fashion MNIST, it contains not numbers, but it contains different type of clothes. Okay, for example, dress or pants or shoes, as you can see here. Okay, so it is considered as a drop-in replacement for the classic MNIST dataset. And you can find the fashion MNIST into this GitHub repository, okay, with all the details if you want to read more. And you can also find the MNIST dataset into this Jan LeCun website. But of course, these two datasets are already built into Keras and TensorFlow. And we will see how we can load them without requiring to download these zip packages. Okay, but just by downloading them from the Keras dataset modules. And these datasets are used like Hello World examples in machine learning programs for computer vision. Okay. So this guide uses fashion MNIST for variety because it's slightly more challenging problem than the regular MNIST. Both datasets are relatively small and are used to verify that an algorithm works as expected. They are a good starting point to test and debug code. Okay. So we have 70,000 images. We will divide them into train images and test images. So we are going to use 60,000 images for training and 10,000 images for testing to evaluate the accuracy of the classifier. And as already mentioned, the fashion MNIST is already available in TensorFlow. Okay, so you don't need to have it locally on your hard drive, but you can use Keras, and this means tf.keras datasets and fashion MNIST. Okay, so if you go to Keras.datasets, you will find here there is a page that is called Keras.datasets, and you have the different datasets available. For example, you can download in the same way the CFAR10 dataset that you have introduced before, CFAR100, IMDb movie reviews, sentiment classification for natural language processing, and several other. MNIST database, this is handwritten digits. And you have the fashion MNIST database, okay, which we are using in our current example. Okay, so you can find all the information about this dataset and also what does it return. So this is the correct instruction on how to load the data from the fashion MNIST dataset. You're going to have two tuples, one that will contain the training images and the training labels, and the other couple is going to contain the testing images and also the testing labels. And these two are actually a uint array of grayscale images. So this is a NumPy array. It's going to generate NumPy array here and the NumPy array here. Same thing for the test as well. Okay, so we are using the same method to collect all the data from the fashion MNIST dataset using this command. And here we're collecting the training data and the testing data using the function .load data here. Okay, so what does it return? Loading the dataset returns 4 NumPy arrays. The train images and the train labels arrays are the training set, the data model used to learn, and the two other data is for test images and test labels as well. Okay, so the images are 28 by 28 NumPy arrays, two-dimensional images with pixel values from 0 to 255 because they are grayscale. So here we have only one channel because it's a grayscale image. It's not an RGB image. If we have an RGB image, we will have a three-dimensional NumPy array. But here we will have only a two-dimensional NumPy array, okay, that contains values between 0 and 255 in the grayscale. And the labels are integers ranging from 0 to 9. Okay, so label 0 corresponds to t-shirt, label 1 corresponds to trouser, label 2 corresponds to pullover, label 3 corresponds to dress, and the label 9, ankle boot. Okay, so these 70,000 images are labeled according to these 10 label classes. And each image is mapped to a single label, whatever in the testing or in the training. And since the class names are not included with the data set, so we can create a simple array, okay, where to put the class names. For example, this is the class name at index 0, the class name at index 1. So later on, if I get the index integer value, I can know what is the corresponding class name. So we will use this later on for the predictions. Okay, so we make sure that the index of every class name corresponds to its correct label here. So we can print class name 0, it will give t-shirt top, and class name 7, it will give sneakers here. So this will make it possible to retrieve the name of the class from the index of the class or from the label, the integer label. Is it clear so far? Okay. So first of all, it's always good in any classification problem or machine learning problem to make sure about the dimensions of your data. Because any problem in the dimension, it will be a problem for starting the training. You can have errors and so on. So we need to make sure that the dimensions are correct, are consistent. And for this, we use the shape function to know the shape of every image. So here, train images.shape, it will return the shape as 60,000. This is the number of images in the training data set. And this is the width and the length of the image, or the height of the image. So here, we will have the training data as a 3-dimensional NumPy array, where it has 60,000 images. Every image is a 2-dimensional NumPy array. So in total, we have 3-dimensional NumPy array. So M, what we call M in the lecture, is here 6,000, the number of training examples. And the shape of the training label, okay, because for every image you have one label, it will be 60,000, an array of 60,000 values. So same thing will be for the testing data. It's only 10,000 and by 28 by 28. And here we have 10,000 for the testing labels. Of course, it's always good also to know what is the type of these variables, train images or train labels. So you can see here, if I apply the method type on train images, train labels, or even test images and test labels, it will indicate that this is a NumPy array. Okay, so always the images are stored into a NumPy array structure, because NumPy array provide a lot of functionality like vectorization, okay, and operation over matrices, multidimensional arrays in a very easy way and a fast manner. Okay. Okay, you can also use the length of the NumPy array to check the length of the training labels here. It's going to give 60,000 for number of training labels. You can actually also print the training labels. Okay, if you print them, you will find an array that contains labels between 0 and 9, because we have 10 classes and the type is unsigned integer, encoded on 8 bits only. Okay, so here we use the shape. We have already used that, the test for the shape and so on. Okay, so now we have verified that our data is correct in terms of dimension, and it's always good to visualize the data before starting to work on it. So we can visualize a sample of data, and here I define a method that is called print image, okay, or display image, which take a data set, a label, and an image index. Okay, so then I will call the print image by applying the data set is the train images that I have defined here, okay, and the train labels, and also I will specify the index to be 0. So you can see at index 0, you will have this image. You can change the index, and you can have here its corresponding label, 9. Okay, here I printed only the label itself. We can print the class. Okay, how to print the class here? The class name. Yes, I can make class names. Okay, label of this index. Okay, so it will say ankle boot. If I change the index here, 5, okay, this is a pull over. Okay, you can change here. So you may want to check several values, okay, to have a look at your data set before starting. So let's have a deeper look at the print image. So here we are going to use matplotlib, and remember that in the beginning we have imported matplotlib.pyplot as PLT. So we are going to use PLT here as the object to plot. So first of all, we need to create a figure. This is the canvas where the figure is going to be displayed. And then we can use imshow, okay, plot.imshow, and here dataset image index. So I will print, or I will show the image located at a certain index into the dataset that is provided as an argument to the method. And here's some additional stuff that I can do on the plot, like for example, color bar or grid. I can remove this. This is optional. So you can see I don't have here a color bar. Okay, or you can put it back if you want. Okay, it will show it. So this is if you want to add a few more options onto your plot. And then show the whole plot here. And finally, I will print the label at the index and the corresponding class name. This is how to visualize the data using Matplotlib. And of course, you should have the ability, if you have any other data set, to display the data that you need in this data set. Okay. So what is the next step here? Yeah, this is normalization. Okay, so we normalize by dividing 255. Okay, for the train images and the test images. What is the purpose of normalization? Yes, it makes the conversion faster. So by making the values between 0 and 1, okay, so it will reduce the discrepancy and the variance between the values. And this will help to make the training algorithm converge faster to the optimal solution. And then we verify that the data is in correct format. We can also, instead of plotting one value like here, we can plot multiple values. For example, here I can plot 100 value from the data set, okay, to have a variety. And this, for example, can help you to check that your labeling is correct. Okay, you can print a first sample of images and check whether the labeling is correct, because sometimes we can do some errors on the labeling. صح ولا لا? Okay, so for example here, you can change, for example, if you want to print less, you can print only 25 and make step of 5 here, step of 5 here. Okay, so you will have a sample of 25. You can even make the dimension of the figure smaller by changing these values. Okay, so this gives you the ability to show a sample of images and check the correctness of the labels. Okay, and here we use Matplotlib, like before, to define a figure, and here we specify the figure size as an argument, and then we use a for loop to print all the different images and their labels using a subplot. So here, this is a subplot that is located at 5, 5, and here I+1. Okay, so it will print row by row until reaching 25. And look here, for example, if I remove CMap, I put only binary visualization, okay, black and white. So if you remove it, it will show it in this way. So you can impose to be black and white by making CMap. CMap, it means the color map binary. And this is going to give you the following display. Okay, so now our data is prepared. We have pre-processed our data. We made the normalization. We displayed the images and we displayed the labels. Everything looks fine. Now it is time to build our model. So we are going to use neural network, the library of Keras, to build our neural network model. And building the neural network requires configuring the layers of the model, then compiling the model. So you remember, we have implemented neural network from scratch. It was very difficult and tedious. But now you can see with Keras, it becomes quite easy. So you just need to describe your model, and all the dirty stuff like forward propagation, loss computation, and backward propagation on these different things will be evaluated under the hood. So you don't need to care about all this level of details. You just need to describe your model as a sequential model here. Okay, so we're going to create a model using keras.sequential. So keras.sequential, it provides you a mean to define a sequential model. It means layer by layer. Okay, so the first layer here, because neural network only take one vector at a time, so we need to convert our input to a flat vector, not a 3-dimensional NumPy array. because the original input is 28 by 28, and you have 60,000 training example. So we need to flatten it to provide the input, okay, as one-dimensional vector. So I will flatten every image of 28 by 28. This is the image size. And here there is nothing to learn. It's just converting the NumPy array into one-dimensional vector. And then we will define another layer using the ReLU activation function. And finally, because we have 10 classes, we're going to make another fully connected layer with 10 classes, because you have 10 classes here. Okay? And you can use model.summary to find the number of your parameters here. So in principle, this layer is a softmax. It's possible to write activation equal softmax like this. But in this example, we are going to make it a linear activation, and I will put the softmax later. You will see in the prediction, at the prediction. Yes. This is the number of nodes in the first layer. Okay. So this is the input. This is the first hidden layer, and this is the output layer. Okay. So this is input. This is first hidden layer. And here you have an output layer with 10 possible classes. Is it clear? Yeah. Okay. So this gives you the number of parameters. So there is no parameter to learn in the input layer because it's the input. And this is the shape. What is this shape? It's 28 by 28. If you make 28 by 28, you will find 784. And there is no parameter to learn. Just we change the shape of the input from NumPy array to one-dimensional vector. And then you have the dense layer, and here you have 128 nodes. So this will give you 100,420 parameters to learn. Okay, how did we get this? Because it is a fully connected layer. Okay, if we, 128 times 784, this will give 100,352. Okay, and what we should add? We should add 128 because we need to add 128 biases. We have one bias value for every node, صح ولا? So if you add 128, you will find 100,480 parameters. And the last layer, that is the output layer, you have 10 parameters, okay? And you will have 1,290 parameters. How did we find this? You are going to make 10 multiplied by 128. It will make 1,280. And we add 10 values for the bias. It will make 1,290 parameters. Is it clear? Yes. The output shape. Yeah, because it's one-dimensional vector here. Okay, one-dimensional vector that is 128 values only. So here you don't have. Sometimes you don't put anything, sometimes they put none here. But it's one-dimensional vector. It means one-dimensional vector. It's just a notation like this. Is it clear? Okay, so now we have built our model. And the next step after building the model by keras.sequential is to compile the model. Okay, you can compile using the compile method. And here you need to specify 3 important parameters or argument. The first is the optimizer. And you have seen several optimizers, like for example, Adam optimizer. And Adams, as you remember, it combines RMS prop and also momentum. You remember this? Yes. And then you have to specify the loss function. Okay, so here, what do we have? We have 10 classes as output, and these classes are categorical classes. They take value between 0 and 1. Okay, they take discrete value between 0 and 1. And pay attention to how do we express the loss in this example, because in the next example about hand sign classification, we will use the similar classification, but we will do it in a different way. So if you remember in a previous lecture, I have talked to you about hot encoding. You remember what is hot encoding? So we have a class classification. Okay, مثلا if I have cat, I will encode it 1 0. If I have not cat, 0 and 1. So here, did we use any hot encoding? We did not. So we used just the integer numbers as the output. In the next example of hand digits, we will use similar things. We will classify hand digits from 0 to 6, but we are going to model the output, not integer values between 0 and 6, but we will use hot encoding. And in this case, the loss is going to be different. Okay, look here, it's categorical cross entropy loss, and here we have sparse categorical cross entropy. Okay, so if you don't use hot encoding, you use this one, sparse categorical cross entropy, and in the next example, we will use hot encoding, so we will use only categorical cross entropy. This is just something just put in mind, and later on we will see in the hand sign example. واضح? Okay. So here you specify the loss. It's the cross entropy loss applied to categorical classification, because when we have binary classification, we use the binary cross entropy, and here we use the categorical cross entropy loss function. And it's already defined in tf.keras. Look, in the tf.keras, you have a package that is called losses, and it defines different type of losses here. Okay, we can check the keras losses, and you will find different type of losses. You have binary cross entropy, if you have binary classification, true or false, cut or not cut. You have categorical cross entropy, compute the cross entropy loss between labels and prediction. And we have here the sparse categorical cross entropy, computes the cross entropy loss between the label and the prediction. So as I mentioned to you here, if we don't use hot encoding, and here if we use hot encoding. And there are different also type of losses that can be used depending on the use case. Okay, and finally, you specify what are the metrics that you would like to track during the training. Okay, here because we are dealing with a simple classification example, we are going to track the accuracy as long as the training is moving forward. Okay, so we would like to print at every step the accuracy value, like you see here. Okay, we would like to, if you put metric equal accuracy like here, it means at every epoch, it's going to print you what is the accuracy for the model at that epoch. So this is the model.compile, model.compile. So model.compile is going now to prepare the model, and the next step is to run the model, okay, or make the effective training of the model. So training the neural network requires the following steps. First of all, you will feed the training data to the model, and in this example, you will use the train data and the train labels array. The model learns how to associate images with labels. You ask the model to make prediction using the test images, and also verify that the prediction are correct. So these are the different steps. Now the first step is to train the model, feed the model. And for this we use the method model.feed. Okay, model.feed. It will use the training data and the training label for the specified number of epochs. Here I'm going to specify only 10, but you can specify 10 epochs or more epochs. And then the model is going to train. So maybe I didn't make compile. Okay, so after compiling, it is now training. We have to wait some time. Of course, here the data set is small because we have small images, so it can work even on a CPU. I'm running this on my Mac. But usually, if you have large images and large data set, you will need to run this on a GPU. If you don't have a GPU, you can use Google Colab for running some training. Okay, so here we will wait for 10 epochs. You can see that the accuracy is increasing and that the loss is decreasing as long as it moves forward. Okay, this is the last epoch now. And now the model has finished. I don't know why I have done, yeah. Of course, like we did before with the cat example, we can save the model into a file and then we can load the model to make predictions. So we need to wait a little bit because I mistakenly have redone the training. Is it clear now, the whole steps? Okay. Okay, hot encoding, let me show you. When we work in classification, the output must be numbers, okay? So for example, in the case of cat and not cat, here we have cat class and not cat class. So we have to convert them into numbers. You can, for example, convert them to 0 and 1. That's one possible way, like we did here in the fashion MNIST. We have labels between 0 and 9. But a better way that is more recommended in deep learning is to encode them into like vectors. Okay, so for example, here you have cat, you can encode it into 1, 0, and the not cat can be encoded into 0, 1. Now, if we would like to make hot encoding for the fashion MNIST, okay, here are the labels. So here the labels, we didn't make any hot encoding. But if I want to make hot encoding, I would say that 0 will correspond to a vector 1, 0, 0, 0, 0, 0, 0, 0, 0. How many zeros here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I will add one more. Now, in this case, I will make 1 equal to 0, 1, 0. So this operation is called hot encoding. Okay, or one hot encoding. So here I will put 0, 0, 1, and all the other things are 0. So we will have a specific vector for every class, because at the end, when you return from a softmax function, it will return a list of probabilities for the different classes. صح ولا لا? So the sigmoid is going to return a probability for every class. So here you can say if it is a cat, probability is equal to 1 for cat and 0 for not cat. If it is not cat, probability is 0 for cat and 1 for not cat. So this is with certitude. But now, when you will do the training, you will find an output like this. 0.1, 0.01, and let's say 0.33. Okay, and then what you will do, you will try to find the index of the maximum value. Okay, so here when we do hot encoding, okay, we are able actually to prepare the data for this kind of output format. This is just to give you an intuition. But of course, we can also use integer numbers like we did here in the labels. But if you want to convert labels into hot encoding, you can do the following. واضح الحين؟ With hot encoding, it may have a better performance. Okay, so for example, here in this example, we are going to use hot encoding, and you will see what will be the difference with respect to this example. Because to train a classifier, there are different ways of doing that. So that's why I provided 3 different examples. So every time we can switch from one technique to another. And then when you want to do your classifier, you can choose any of these techniques. Okay. So coming back now to our model here. We have finished the training. Yes. What does what? Epochs. This is the number of iterations. Yeah, number of iterations. Yeah, and we talked about epochs in the lectures, if you remember. So every epoch, it means you have used all the training examples into forward propagation and backward propagation. This is one epoch. Okay, and then you calculate the loss, you make backward propagation, this is one epoch. The second epoch, you make forward pass, calculate loss, backward propagation, this is the second epoch. and so on. And you repeat until the number of epochs reaches a certain number, or you will stop when the accuracy reaches a certain level. Yeah, there is no actually main rule. You can actually track the accuracy when, for example, the accuracy is not changing for 10 iterations, you can stop. You can, for example, say, I would like to train for a certain number that you know in advance. There are different techniques. If you remember in the problem of prediction of house prices, we made the early stopping, okay, if the loss is not going to decrease during the 5 last iterations. So there are different ways on how and when to stop the training. In this simple example, we mentioned that we want to stop the training after 10 iterations. But there are also other conditions that we can use on which we decide to stop the training. Okay. So you can also save the model.save, my fashion model.h5, for example. Okay, now the model will be saved. If you open the notebook, you will find my fashion model, and it has 1.25 megabyte. It contains all the parameters, 100,000 parameters, 770 parameters. Okay, now the second step is to evaluate the accuracy of the model. So I would like to stop here for maybe 20 minutes. We go for prayer, and I want to finish after the prayer because there are still things to explain. واضح? So we will resume after, inshallah, maybe 20 minutes. So we have completed with training the model, and as already mentioned to you, you can save the model into the hard drive so that you can load it later on, as we did in the CAT training example. And here, we would like to evaluate the accuracy of the model using the test images. Okay, so in this case, we can use the model.evaluate, the method model.evaluate, which is available in TensorFlow Keras. And here you have to provide the test images, and you provide the test labels. And verbose here is equal to 0 or 1. So 0, it means you don't want to see any intermediate output. And verbose equal to 1, you will see all the different output during the evaluation of the model. So I just put it 0. At the end is going to print the accuracy found. So now, doing that, we can find the training accuracy. So in this model, I don't know if I have changed anything, but in principle, we should have something like around 91% here. But in the previous training, it was only 86%. Anyway, we can look that the training testing accuracy is a bit less than the training accuracy, although this is normal, but it may also lead to having some kind of overfitting, because usually the data performs better on or the model performs better on the data that it has used for training rather than the data it has used for testing. So we have here in this particular example, we have just a little bit of overfitting, not that much, which could be acceptable. But of course, if the gap is large, for example, if we find something like around 70% or like this, in this case, we will have a big problem of overfitting, and you have seen in the previous lecture about structuring machine learning project, how to deal with overfitting problems and how to solve that, maybe by doing data augmentation or some more optimization into your model. Okay. Now we would like to use our model to make predictions. Okay, so in this example here, we're going to create. We will add to the model just a softmax layer here. And it's possible to add this softmax layer also inside the model before the training. But in the example of the tutorial of TensorFlow, they didn't use the softmax function during the training, but they have used at the end here during the prediction. And always are possible. I have just to run the softmax function inside the training model. I got a little bit of less accuracy. And you can try this. I put here a second model that I've called the classification softmax in the model. What I did, I have just added this softmax layer here. Okay. Yeah, and I think you will see that here it has given a little bit less accuracy as compared to the original model of the tutorial. So the difference is that here we just put a fully connected layer with 10 neurons at the end. And here I have tried to add a softmax activation function. So if you don't put softmax here, if you just put without any activation function, this is equivalent to having activation equal linear by default. And you can see this into the sequential model of Keras. Look, this is the documentation for the dance layer. And by default, if you don't put any activation, none. In this case, if you don't specify anything, no activation is applied. So it will be linear. It means the activation of x will be just equal to x at the end. Okay, so no changes. So it turns out when I did here the activation function equal to softmax, I got a little bit less accuracy, but nothing prevent to try this with more epochs and probably a little bit of different configuration, because what looks more reasonable for me is to have an activation function of type softmax at the end. But I found that in the tutorial here, they put just a dance layer with a linear activation function at the end. And they have used here the softmax function as an additional layer after finishing the training, okay, to make the prediction. So now let's call our model with softmax as a probability model. And this is going to convert the output into a probability. And it means that it's going to sum to 1. So let's make prediction, probability model.predict. And also, I can make another prediction. Let me call it prediction 2 equal model without the softmax dot predict test image. Okay, both are accepted. We can now print the prediction value here, just to compare. This is the prediction value, and I'm going to print the second prediction value as well. You can see that there are differences. If I try to apply the method sum, look at here and look at here. The sum here is equal to 1 because the softmax function is going to normalize the output such that the sum of all probabilities, because the softmax function is going to consider what is the probability that that the object corresponds to that class. And of course, the sum of probabilities is equal to 1. However, if we just use the model itself without the softmax, okay, the sum of values, so this corresponds more to a score rather than to a probability. That's the difference. Okay, does this make sense to you? Okay. But you will see later on that in the hand-digit example here, the last layer was actually a softmax layer. Okay, just to tell you that, and in this case, you don't need to make for the prediction, you don't need to make this additional softmax at the end. Okay. Now, having understood this, let's move forward. So we want to make a prediction. Let's take an image. So I will take an image of index 5 from the test images. I will use the method print image that I have defined in the beginning of this tutorial here. If you remember about this image, yeah, this is print image that we have used to print the train images. Now I will use it to print the test images by just changing the dataset to test dataset and test labels to print the test images. So print image here, put the test dataset, the test labels, and the image index. So this is the ground truth class name. It's a trouser. Now I would like to know whether my model is able to predict correctly this image as a trouser, because trouser here, this is the real class name. So what I will do, because predictions here is what? Is a multi-dimensional array, okay, of 10 multiplied by the number of test images. So I'm going just to select the prediction that corresponds to the image index equal to 5. And this is what is going to return. It's going to return an array of probabilities. Okay, so the probability that this image corresponds to label 0 is 0.099. And the probability that this image corresponds to the label of index 1 is 0.0996, and here 99.8, and so on. So what we will do, we will try to select the index that corresponds to the maximum probability. Okay? So we will use mp.argmax, and we apply here the whole array of probabilities, and it will return the index that corresponds to the highest value. Okay, so here it makes a wrong prediction. So the problem here is that I need to, let me take some time to restart the whole model, because I think I have executed this in several iterations, so the model did not train correctly. So I'm going now to train the model of Keras, and in principle we should find 90% of accuracy. Just let me wait a little bit until this finishes. Look, now the accuracy is going toward 0.9. But before, when you work in Jupyter Notebook, if you execute multiple times the cell, maybe it's going to take some intermediate values that will change the output. That's why it's always better that you run the kernel, you clear the kernel, and then restart everything from zero. Now we're going to have the expected output. But I'm not going to change anything in the code. Okay, look now, we find the correct accuracy. That is 91%. Okay, fine. Okay, these kind of issues you can find them. And look now, the test accuracy was found to be 0.88. So here we have less, and this might be due to overfitting. Now going back to our prediction. Okay, so look now, I found the class index equal to 1. This is the predicted, and this is the ground truth. The ground truth, it means the correct label. واضح? Okay, so how to find the correct label is by finding the index that corresponds to the maximum probability in the output of the softmax function. Okay, and you can do this with the, so you can play with this. For example, I will choose, and it's not necessary that every time you're going to find the correct prediction. Don't forget that here we have almost 88% of accuracy on the test class. But we can try some other ones. This is a trouser. Let me try something different from a trouser. Sandal here. Okay, so it's the ground truth is 5, and now it makes a correct prediction. You see, it has made a correct prediction. Make another one. This is a bag, and it makes a correct prediction. So you can see the predicted class label is the same as the real class label, and this is what we want to do. Okay. Now, these are two utility functions that we use to plot the image, okay, multiple images. If you want now to visualize the output of your classifier for multiple images, you can look at the content of this method here. And we will use these methods to verify the predictions. Look here. This is for I equal to 0. You make one figure, okay, and in the first subplot, you will put I. You will put the prediction of I, and test label, and test images. So this one has given a correct label. Look, it has very high probability for the class equal 9. Class 9, it corresponds to Angleboot, the last class. And here, okay, here it made a wrong classification. Okay, for 12, it makes a wrong classification. It's a sandal, and it has confused the Angleboot to a sandal. Okay, and then you can try different ones. So here, for the code, it makes it correctly. Okay, so we can plot several images with their predictions to see what it can find as wrong. And here you can see that out of how many images here? We have 4, 1, 2, 3, 1, 2, 3, 4, 5. 5. So we have 15 images. He has made 15 correct classification and 1 wrong classification. Okay, so this is a way to check, visualize the output of your classifier for some unseen images. And of course, you can also use the trained model to make the there is some noise. You can use the trained model to make the prediction over a single image. Okay, so here we can select an image, for example, the image at index 1 from the test data set, and we can visualize its output. It's 28 by 28 like any other image. And if you remember here, we didn't have to resize the images because all the images have the same size. But of course, if you work with other data sets, usually the images comes with different sizes. So in this case, you have to decide what will be the input size of your neural network, like what we have done into the cat classification. So in the cat classification, we have resized all the images to fit a single image size, okay, specified in advance. But here, this data set contains all images 28 by 28. Just a small parenthesis here. And of course, if we want to use a single image to predict in the trained model, we have to expand it. Okay, and here it means it's like we do flatten for the training. So we are going to change the dimension. We can make reshape, or we can make np.expand dims image, and here 0. And you can see it has converted this image into the following shape. And we can use this shape to predict the label for this image here. Okay, so now we make prediction probability model.predict img and print predicted single. So of course here it will use the softmax function to generate all these probabilities, and we can use argmax, so it will print 2 for this one. What is the correct label? We can check the correct label of this by printing print test labels at index 1. So it's 2. So here the prediction was correct. The prediction was correct. Okay, I hope now with this example you got very detailed information about a classification project. So I went with this into all the details. I was preparing also to make another example on a very exciting example about hand gestures, how to recognize hand gestures like this. And in this example, we will use hot encoding. So inshallah, I'll try to coordinate with you maybe tomorrow or after tomorrow. Tomorrow you have lectures, afternoon, or you have any lecture? No problem. Yeah, no problem. I will try to coordinate with you. Maybe I will make a doodle link, try to coordinate you one lecture to provide you some more details about this. Okay, but I hope that you try to make the example again by yourself. Try to change, try to read from the documentation of Tensorflow 2 from Keras, okay, to get familiar with all these different instructions and functions. Okay, do you have any question?